I think I happen to find the discussion of operation and human factors to be fascinating from a railroad operations point of view. We will actually do a little bit of engineering when we get into the stopping distance part calculations, but what can go wrong is amazing. So let me start off by showing you a video. In fact, today I'm going to be showing a few videos, and I'm going to sort of talk a little bit about this video, and we'll come back to it. But this one particularly incorporates a few interesting things that we've already seen before. So let me see if we get this to work properly. It's going to repeat again.
This one was in Spain, isn't it?
That's right. This one, if you let's go back to
famous crash.
Yes, it's a very famous crash. That's exactly right, and it was in Spain. See, Spanish high-speed train derailment, July 2013. Do you remember what the cause was? The driver was on the cell phone.
High speed.
High speed because the driver was on the cell phone.
Oh.
The driver was busy. Yes, he was. I'll talk about the details a little bit, but basically, he took this curve about double its allowable speed. So he was going into this curve about double the allowable speed. The driver was on a cell phone. But one of the things I want to point out for you, I want you to look at this again and watch this lead locomotive. You can see the trailing bogie is going to be the first one to climb. So just watch this again. Let's just, I can skip some of this stuff here. Watch the trailing bogie of the lead locomotive. Okay. Now, hopefully you all remember what we talked about the Nadal limit and wheel climb and all those good things. So this was a high-speed derailment due to the driver being in the cell phone, but the engineering reason, the engineering behavior that you're seeing here is a high L over V induced wheel climb. Okay, so what was happening is because he was going too fast, the lateral force. Hopefully, this may have to stretch your memory a little bit because we talked about this in a back last summer. We talked about lateral loading and we talked about centrifugal forces and curving forces and all those good forces. So here you had a case where you were over speed. So your centrifugal force was very high, which generated very high lateral loads. So your L over V was very high and you had a high wheel climb. And that's exactly what we talked about last week when we talked about the Nadal limit wheel climb. I like to show this because, first of all, it's a video. You can actually see it, but you can actually see that rear bogie climbing. This is one of the very few accidents I've ever seen actually recorded on tape, where you can actually see that rear bogie climb. And so I find this fascinating to do this. We're going to come back to this, but this is sort of I figure I want to catch your attention a little bit when we start this class. How, although this was a human factors problem, this was a classic human factor problem, which was the let's see. which was the driver on the cell phone. But just the same, it has a well-defined engineering behavior to it. So let's see if we can get this going. And that's what I was afraid of. For some reason, when I do it this way, it doesn't let me put a marker on here. So let me just stop sharing and come back and do it this way. Huh. Oh, there it is. Okay, so we're going to start talking about human factors type of accidents. And human factors accidents include a whole slew of activities, including drug and alcohol, incapacitation due to injury or illness, literally the classic heart attack that happens when the driver's there. In the metro world, we have a dead man switch, we call it, which is designed to prevent anything from, if something happens. We have alerters in the railway system, and now, of course, we have in the modern world, we have train controls. We have positive train control. We have the train control systems, all of which we'll talk about there, and that prevents some of these that we're going to talk about, but not all of them, depending on where and how you're working there. Employee restricted in worker motion, employee asleep. This is actually a big problem in the freight world, where train drivers have very varying schedules, and they often don't get enough sleep. And there are issues we'll talk about there. And then employee physical condition, I'll give you a couple of interesting examples of how that works as well. Okay, the good news is the number of accidents that you tend to deal with these human factors is very small, but when they happen, they can be quite significant, with significant numbers of fatalities. And you can see here, this is some of the European data dating back to the 2005 to 2010 range. And you can see, for example, how significant human factors is in the British way they assign responsibilities. So have all sorts of human factors type of accidents. We'll talk about this one a little bit later. This is what's called signal past that danger, when you pass a red signal. Again, nowadays there's technology that's designed to prevent it, but it's not 100% foolproof, as we'll show in about a minute. Okay, so in some parts of the world, it's called positive train control, or PTC. In the UIC world, or at least in the European world, it's called European Rail Traffic Management System, and more specifically, the European Train Control System, the ETCS, which I believe Israel Railways is introducing into quite a few of its lines, at least at some level. And metros often have a system that's called an ATS, or an automatic train stop system, which is a little bit different technically from either a positive train control or an ETCS type of system. But they're all designed theoretically to stop the train if the train is going too fast, if the train goes past the red signal, if there are certain clearly well-defined criteria that are exceeded. And for the most part, they work well, but they don't work 100%. Okay, Just a quick refresher on ETCS. ETCS really has multiple levels, starting with level 0, where you basically don't have any technology associated with the interface between wayside equipment and the locomotives or the locomotive drivers. And then ETCS level 1 is where you start having some line side equipment, some wayside equipment, some signaling type of systems that provide information back to the train driver and back. Usually level 2 already is where you start imposing a automatic stopping of the train. And level 3 is where you're actually not even relying on trackside equipment, such as track circuits or axle counters, but you're relying more on GPS type of systems. So various European railroads are moving in this direction. Not a whole lot are really at level 3 yet, but there are a lot of them that are moving towards level 1 and level 2. Okay. So let me give you a couple of examples of some accidents. Just I want to sort of set the stage here to discuss some of these accidents. Now, again, some of these accidents you'll see are pre-positive train control, ETCS type technology, and some of them are post-positive train technology. And we'll talk a little bit about where the positive train control, ETCS type of technology, which is designed to stop trains from overspeed. So, for example, the Spanish accident that we saw before, if a proper ETCS or PTC or ATS type of system was in place, it would have been detected the overspeed, even though the driver wasn't paying attention, and would have automatically slowed the train or even stopped the train before it went into that curve. So that's the kind of technology that we're moving towards to get us away from the driver, because when there's a driver who's controlling the train, we know there's a potential for a couple of accidents can happen. Okay. So this is a 2014 German accident. By the way, I've sort of culled my presentation, got rid of a lot of the American accidents and put a much larger share of European accidents in here, just so that we don't constantly point to the Americans and say, well, the Americans are crazy anyway. They don't do a good job of running their trains. In this particular case, a freight train passing through Mannheim Station crashed into the side of a passenger train. And so there were no fatalities per se, but there were 38 injuries, 4 seriously, 2 cars derailed. You can see the engine. You can see 2 of the cars actually were overturned. I think 4 cars derailed and two cars were overturned. 5 cars derailed. Okay, 5 passenger cars, two overturned. Those are these 2, and then a bunch of the freight cars as well derailed. Again, you can see the accident. Lots of nice pictures of there. Okay, so what happened here was the freight train didn't pay attention to a red signal. The driver had lost his position. And by the way, this is not an uncommon characteristic for these kinds of accidents, where the driver gets confused about where he is. And by the way, that's not confined to railroads as well, as I'll show you a couple of later. There have been some metro accidents and some commuter accidents where the driver has sort of lost his bearing, has lost his location. And so he, for example, didn't know there was a curve coming up, or didn't know there was a red signal coming up. In this particular case, he was expecting the signal to be on the left-hand side because he thought he was somewhere else, instead of the signal being on the right-hand side. So he doesn't look at it. So in this particular scenario, since this is Germany, there was, in fact, a train control system in place called a PZB safety system, which is an automatic stop system. So the PZB system is a system where if you pass a red light, it basically forces the train to stop, and it did, and forced the train to stop. So what happened here? The train stopped. So in this particular case, the driver, instead of contacting the dispatcher or the train controller for instructions, which was what he was supposed to do, he restarted the train and just kept going. Even though he was stopped, he just restarted the train and kept us going, passed a couple of more signals that were not guarded by the PZB, because particularly in yards, you don't always have train control or train stop in every signal. And then he hit the Eurocity train. So the PZB system was one of the first was an earlier generation ATC, ATS, automatic train stop system. Sometimes you also see this called ATC, which is automatic train control. By the way, does everybody see the yellow here, or do I need to switch color? Hopefully you can all see the yellow.
Yes, we see.
Very good. Okay, so in all of these type of systems, again, what happens is you usually, if you pass, usually a lot of these are designed to be passing a signal, and the German PZB system is an example of this. So you pass a signal, it sets off alarm when the driver is getting to the red signal, and then it just applies the brakes automatically. So it's in general a good system, but in this particular case, the driver was able to, once he was stopped, he was able to restart. And by the way, a lot of the positive train control or ETCS systems have that feature where the driver can override, after he stops, he can restart, he can override the signal. And there are a couple of reasons for that. Sometimes the driver needs a special code to do that. But I've been in the cab of an ATCS of a PTC locomotive, positive train control locomotive, the higher generation ones, where the driver can restart and move and restart and move and restart and move. Sometimes he goes for a shorter distance, sometimes he goes for a longer distance, depending on how the system's designed. So in this particular case, there was about 2.3 million euros worth of damage, as you can see from the picture. The driver was convicted for intentionally endangering railway operations because of negligence, because he restarted the train without asking for instructions, even though he had been braked by the system. Instead of calling the dispatcher or the controller, he just went ahead and restarted it. In this particular case, he received 6 months probation and 100 hours of community service. But the point was that the driver was criminally convicted in this particular one. Okay. High-speed passenger train collision in Turkey, December 2018. High-speed passenger train and a locomotive collided near Ankara, Turkey. 3 carriages of the passenger train derailed. 3 crew and 5 passengers were killed, 84 passengers injured. Later, another passenger died. It was a serious situation. Again, you can see, this is a very modern system. This actually system had restarted, had just started. And you can see how modern everything looks over here. This was a straight head-on collision. What happened is that there was a locomotive coming back doing track inspection, and the locomotive was actually on the right track, but the high-speed train, which was in this particular case was going to about 80, 90 kilometers per hour, was on the wrong track. He was basically going this. He was going an opposite direction to the inspection locomotive, and he caused a head-on collision. So what happened here? The railway line was open to traffic before the train protection system was fully operational. I will show you that's happened a couple of times. There are one or two other examples that I have along the way here where exactly that happened. Either they thought the train protection system was fully operational, it turned out it wasn't, or they knew it wasn't fully operational, but that because of political or scheduling or other reasons, they decided to go ahead and start operations. And so in this particular case, in this Turkey collision, again, this is recent, this is 2018. This is only a couple of years ago. The train protection system was not fully operational. Okay, here's a German 2017 example. In Meerbusch, Germany, a passenger train slammed into the rear of a freight train. 50 people were injured, 9 seriously. In this particular case, the driver of the passenger train was able to give a warning before the collision occurred, but the train didn't stop. Okay, so the freight train again was on its proper track. It's been what they think happened here was that the passenger train was given permission to pass a stop signal. So he should have gone at very low speed, 40 kilometers per hour, so that he should be able to stop within sight distance. But in this particular case, the rear of the freight train was not well illuminated. There was poor visibility, and he passed the signal again. So again, this is the situation where you can have a positive train control or an ETR, European Train Control System, or an ATS system in place. But because most of these systems, and for good reason, because there are some times where you really do need to pass a red signal. What happens if a red signal is faulty? What happens if the red signal is not working properly and the train has to go past? So you have to be able to override the red signal and not stop, automatically be stopped, not go any further, because there are situations where it happens. And again, I've been on locomotives with PTC, with positive train control, so I know you have the ability to override a stop signal with certain codes or certain restrictions. So here, the passenger train was given permission to pass the signal, but and so although there was a train control system in place, he did go past it. But the driver, instead of going at a speed where he can stop, because visibility was poor and because the freight train was not well illuminated ahead of him, he didn't really see it and he plowed into the rear of the train. Again, human error. In the era of train control systems. And here you can see the picture of the train. There you can see the passenger train hitting the back of an empty wagon. You can see derailed a bunch of freight wagons. This is that Spanish high-speed train derailment that I just showed you. There, we just showed you the video, so I'm not going to replay it. That wheel line one. This is 2013. This is before there was a train control system in place. So the train, this was a really nasty accident. 80 people died. I mean, this was one of the worst accidents in modern times. The German broken wheel accident I showed you, we talked about last week, was worse. They had over about 102, 103 people died, but that was also in, I think it was 1999. So this was 14 years after that. Okay, so the train was traveling, the posted speed for the curve was about 80 kilometers per hour. The train was traveling at about 160 kilometers per hour. This was a high-speed rail operation, and we showed you the wheel climb. We talked about that one already. Here's another view of the accident scene. Again, when you see damage like this, it's not good. So 80 people killed here. Another view of the crash site. So again, this should be preventable with modern technology. You can see the different control systems: automatic train protection or advanced train control, ATC, ATS, automatic train stop, positive train control, European train control system. These are all the ETCS. Hold on a second. Somebody's in my. I'm gonna take a 2-second break. Somebody just rang my doorbell. Let's see what something happened. Thank you. Yes, thank you. Sorry about that. Somebody actually was. That's the problem with working at home. The doorbell rings. That was actually a delivery that I didn't even know was coming today. So I apologize. Okay, so I was trying to say ETCS and PTC and advanced train control are the newer generation systems. ATP, ATS, and there's another ATC called automatic train control. And so, it's interesting. There are two ATCs, acronyms, are the older generation type of stuff. So, for example, automatic train stop is a technology you see a lot in metros. But that German technology that I just talked about before, the earlier one also was an automatic train stop. It works very similar. Automatic train stops are triggered when you usually go past a red signal. The automatic train stops and some of the automatic train control systems are more really geared towards passing a red signal, not so much as going to overspeed. The newer generation systems, the ETCS, the PTC, the advanced train control, they also look at speed and take into account speed. So that, again, as I said, the Spanish type of accident should have been, if there was an ETCS or a PTC system in place, that should have been prevented. So again, the driver of that Spanish train said he lost concentration, but when they checked his telephone records, they talked about the fact they saw that he was actually on the telephone, and he was also charged with homicide by professional recklessness and actually went to jail. There was an Amtrak derailment in 2015, which was very, very similar to the Spanish accident as well, except the driver wasn't on the phone per se. This was a case where the driver entered a curve. There was a curve that had an 80-km/h speed restriction, and he entered the curve at about 164 km/h. So again, like the Spanish case, it was double the speed. In this case, only, and I say that very, very facetiously, only 8 people were killed and 200 people injured. So again, it was a nasty one. This was an Amtrak's Northeast Corridor. This was actually south of Philadelphia. I remember this accident very well because I actually was interviewed and had discussions with several news agencies when this happened. Here again, in this particular case, the driver was distracted and lost his bearings. He didn't realize where he was. He didn't realize he was going into a curve. There's a fancy English word for it called he lost situational awareness, which means he didn't know where he was. And there have been other accidents, which, and in fact, I got another one I'll show you in a few moments, also an Amtrak accident, but in the state of Washington rather than near Washington, D.C., where, again, the same thing happened. He lost situational awareness. He didn't know where he was. Again, the frustrating part about this particular operation is it would have been prevented by an automatic train control system. Amtrak had automatic train control systems on most of their railroads, but this particular location didn't have it in place. So in this particular case, where the system was not even installed until it was installed literally a year later in 2016. So I'm not going to go through the details of it. A lot of things were happening. The driver said he thought somebody actually may have thrown something against the windshield and distracted him. But he basically lost his location. He didn't know where he was. So he entered this 4-degree curve at double the speed, 160 kilometers per hour versus 80 kilometers per hour. And again, by the way, derailment mechanism was wheel climb. When you have an overseat situation, that kind of wheel climb with high L over V is usually the actual engineering mechanism that you run into as to why it derails. And, again, pictures. Okay, here's an interesting accident. This is a metro accident. So this was some sort of automatic train control was there. This was, again, very recent. This is 2019. So this was only a couple of years ago. And this was in Romania, in Bucharest. So there was a CIF metro unit failed to stop inside a depot and overshot the buffers. There were buffers at the end of the track. He was going fast enough that he crashed through the buffers. There was an accident in New Jersey, New Jersey Transit a number of years ago that was very similar, where the automatic train stop didn't engage properly, and the train was going fast enough that it overran. The buffers, are basically mechanical blocks at the end of the track, so designed so that you don't go through the track. But when you're going fast enough, there's nothing going to stop a moving train. So what happened here was this was in January, so it was very cold weather. So because it was cold and icy, instead of stabling the metro unit outside the depot, they wanted to bring it inside the depot. So the train, which was being actually pushed by a shunter locomotive. So this metro used shunter locomotives inside of depots. Actually had a runaway. There was an ATCS system, but there was a software failure. And by the way, I've seen accidents, or I've seen reports of accidents where not only we have software failure. I'll recall one accident. I think we'll talk about it here a little bit, where they were actually switching software. So they actually they were in a time gap. Where they were basically replacing old software with new software, and the train control system was not operational. We're not properly operating during that software gap, of installation gap, and the accident happens there. There's an expression in English called Murphy's Law, which is sort of anything that can go wrong will go wrong, and we see that in the railway all the time. So there was a software failure. The ATCS didn't work properly. So the train was overspeed. It overran the buffers, and it actually crashed into the depot. And here's a picture which I find fascinating. So you can see the metro car inside the building, somewhat higher up than where it should be. Because there was no tracks in there that he was supposed to go to. You can see this is just a hall within the depot where the metro vehicle is located. Okay. Another German accident, Bavaria 2018, moving passenger train collided with a stationary freight train. Train driver and the passenger were killed from the passenger train. Dispatcher error in this particular case. The dispatcher allowed the train to go forward. Again, you can see the collision. This is an older accident. This is pre-PTC. So I'm just going to briefly show it because I want to show you a couple of issues here because I want you to understand some of the engineering issues behind it and some of the human factors issues as well. So this is a Burlington Northern Santa Fe. So this is a U.S. freight train. It's actually a 14,000-ton coal train collided with the rear end of a standing, what they called maintenance away train. Maintenance away train is a train that moves maintenance gangs and maintenance gang equipment from site to site. So the maintenance train was standing still and the coal train hit it in the rear. It hit it at about 40 kilometers per hour, but it was a very heavy train. So the rear car, so let me just show you the kind of damage of that impact. This was the front of the collide. So the collision was going that way. This is the front of the coal train that hit. This is the back of the maintenance away train. And you can see how it was just accordioned up here. Take a look at here. You can see 1, 2, 3, 4 different wagons all crushed to each other. So this was an accident at, what did I say? It was 40 kilometers per hour at this accident speed. Yet because it was such a heavy train, it generated that kind of damage. Again, you can see the kind of damage involved. Derailment diagram. I'm not going to go into details. The engineer, the 2 people in the cab of the striking train, of that freight train, were killed. The train, the locomotive of the train that was struck was way up here. So there was, while there were some injuries because of the damage, there was no fatalities on their part. This was about a $9 million collision. So this is a nasty collision. The locomotive was crushed. The entire locomotive cab was compressed so that they were finished. Their amount of survival space was about 65 cubic feet. So what is that, about less than 3 cubic meters, 2.5 cubic meters worth of space left. Again, from the force of the impact. Here, now what was interesting here, let's take a look at the event recorder data. Locomotives have event recorders, which record the braking action of the train. So what we saw here, so this was the direction of the train. This was its speed. What happened now, locomotives, in addition to everything else, have what we call alerters. An alerter is a horn and light signal that goes off if the locomotive driver does not take any action within a given time period. Usually around 2 minutes is the more common one. It's very similar in concept to a Metro dead man switch, except I think the dead man switch time frame is a little bit shorter than 2 minutes. The locomotive alerter, also it's adjustable, but it's really common. So you can see what happened here. So at 6:42, the alerter went off and it was reset by hitting a button. At 6:48, the alerter went off again. So it means basically, that means 2 minutes without any locomotive engineer action. And by the way, locomotive engineers know they have to, if they don't do anything else, they have to hit the button every 2 minutes. 6:53 went off again. And then no activity for 1 minute and 53 seconds. The alerter should have gone off another 7 seconds, but before that, it hit the rear of the train. So you can see there's a pattern. Something happens. The locomotive driver was losing attention here. And what he was literally happening is he was falling asleep. Both the driver and the conductor. There were 2 people in the crew. They were both falling asleep. So this was 6:40 in the morning. You had an issue of crew fatigue. This was before positive train control, which would have stopped this particular problem. There was also issue of the crashworthiness of the locomotive module cab. Remember, we talked about crashworthiness when it came to wagon design. There's also a crashworthiness issue when it comes to locomotive design to make sure that you have a crumple zone, etc. So in this particular case, the crew had fallen asleep. And it turns out that one of the crew members was diagnosed with something called sleep apnea, which is a tendency for people to be not sleep well at night and then fall asleep during the day. And so this was an issue. Okay. I'm going to quickly go through the Chase, Maryland 1987 accident, only because it was a classical accident that led to the introduction of drug and alcohol testing. This was a collision that happened in the Northeast Corridor, where a Amtrak train crashed into a set of locomotives that were running on the corridor. They had run a red light because the driver and the other crew member were taking marijuana. So they were on drugs. This was pre-drug testing. Again, this is well before positive train control. The Amtrak train was going about 174 kilometers per hour, which was the proper speed range. The Conrail locomotives passed the red signal, basically, and 14 passengers were killed. Again, here's the accident there. There's what the Conrail unit looked like. Just like I said, it was a very famous historical case because this led to the introduction of mandatory drug testing in railroads in the U.S., which later spread to the rest of the world. So in a way, mandatory drug testing on railroads stemmed from this particular accident. And I'm not going to go through it other than saying positive train control would have stopped this accident because it would have stopped that train from going through. Okay, another German accident, head-on collision, 2016. 12 people died, 85 people injured. In this particular case, again, you can see the head-on collision. This is not far from Munich, Germany. Okay. Because you can see the accident was on a curve. So the problem with curve is that nobody can see each other, so there was no warning whatsoever. There was an automatic braking system on this line. The problem is with nobody passed. So what happens is that this is again the PZB system. In this particular case, the train dispatcher was at fault. So in this particular case, instead of the cab system activating the system, the train dispatcher basically provided an automatic override to the automatic train control system. So in this particular one, the driver basically got a signal from the dispatcher saying, okay to pass. The dispatcher override the automatic train stop himself. And the dispatcher at that time was playing a game on his mobile phone. So he wasn't paying attention to the situation. He didn't realize there was another train on the coming in the opposite direction. But he realized his error, and then just to make life more difficult, he basically dialed the wrong emergency number. And so he override the signal because he was playing games on his phone, and then he dialed the incorrect emergency number, and so the collision happened. He gave incorrect orders to both trains. He overrode the automatic train stop because he was distracted. And then when he tried to send an emergency code to the train, he basically entered the wrong combination on his computer. Okay, this is a 2008 accident. I'm not going to spend a lot of time on it. This was just a driver on the cell phone again. Drivers on cell phones are one of the modern issues here. In this particular case, let me see if I have the details of it. In this particular case, the driver who was on duty between 6 a.m. and 4 p.m. on that day sent or received 95 text messages. And during that shift that he was actually operating the accident, he actually sent 21 text messages, received 21 text messages, and made 4 phone calls, all in the afternoon, on the day of the accident. Okay, this is another overspeed accident due to driver losing track of where he was. Again, this was pre-positive train control. This was 132-mile-kilometer operation. Train went into a curve that was designed for 50 kilometers per hour. He went to it 136 kilometers per hour. You can see the curve. You can see another wheel climb accident, but again, pre-positive train control, ETCS or PTC, which should be able to control that. And here's one more that I just want to show you because it was a very dramatic one. This was another case where the line was opened before the positive train control was not yet active. This was a brand new operation of a brand new bypass. So they opened up a bypass on this line to shorten the amount of time they take, and actually was supposed to go faster. So in this particular case, the driver again lost his orientation as to where he was. He had only taken this route only once before, so he wasn't even that familiar with the route. So he came into a curve. He came into a curve that was designed for 50 kilometers per hour, and he came in at 126 kilometers per hour. And just because this is my beautiful television footage, this is the Amtrak train. This is the lead. He was going in that direction. So there was a locomotive at each end. He actually derailed on this curve, dropped off the highway, dropped onto the highway, and as you can see from this picture, actually crushed several trucks and automobiles underneath the highway below. So there were about 3 dead, 70 injured, and a whole bunch of automobiles damaged. Again, this was a case where the operation started before positive train control was initiated. Positive train control was available on the other side of this line and on the earlier side of the line, but this particular bypass did not have positive train control installed yet. And they opened up the line because I think it was a political reasons, and they had this accident. Again, you can see how many rail vehicles fell off on the highway.
Excuse me, Professor.
Yes.
What does it mean, driver zoned out?
Driver zoned out means that he lost, he basically, he wasn't paying attention. He was mentally distracted.
Okay.
His mind was elsewhere. And very often when that happens, you have a situation where the driver loses his location, which was exactly the case here. There were signs saying there was a curve coming. There were signs saying there was a speed, slow down, slow down on the train. But he lost his situational awareness. He didn't see the signs. He was just mentally distracted, and he went into the curve at roughly more than double. In this case, about 2.5 times the permitted speed in the curve. Wheel climb, derailment, etc.
Professor,
Yeah.
wasn't a guardrail over there?
Say again?
Wasn't it a guardrail over there?
Oh yeah, there was a guardrail, but you really think a guardrail is going to stop a 1,000-ton train traveling at 126 kilometers per hour?
It seems not.
Yes. Yes. The problem was, yes, there was a guardrail, and in fact, you actually see part of the guardrail through here, but in this particular case, unfortunately, a guardrail will not stop a 126 kilometer per hour train. It's.
I see. Thanks.
Good question. Good point, though. If the train would have been going at 50 kilometers per hour, the guardrail would have stopped it. Maybe at 70 kilometers per hour, but 126 kilometers per hour is just too much energy. Just tears apart the guardrail.
So the problem in curves is speed, mostly speed. We're dealing with human factor accidents, okay? So there are multiple problems in curves, but most of the problems of curves are associated with lateral force and L over V, right? We talked about L over V last week, so you should be familiar with the L over V concept. Okay, so the lateral force is dependent on several factors, speed being one of them. So if you're going over speed, yes, you're generating a higher lateral force. That higher lateral force will cause high L over V, and you'll have a wheel climb. You can also get high lateral forces associated with poor curving behavior. So, for example, if your bogies are not curving properly, again, if your wheel sets, for example, have reverse conicity, so you don't have good steering around your curve, so your axle is not steering properly. If your bogie is misaligned, all of these can also generate high lateral forces. You can also get high L over V if you have low vertical forces. Remember, we talked about last week, actually, we talked about several accidents where the suspension system was not working properly. And so there was an unloading, or there was a non-uniform loading. What sometimes happens when the suspension system is not working properly is that one wheel has less vertical load and the other wheels have more vertical load. So if that one wheel has less vertical load also has a high lateral load, then you end up with a high L over V, and again you have that wheel climb. And yes, the answer is curves are more susceptible. And in fact, we tend to see a lot of problems in the clothoid or in the transition going into or out of the curve, because there you have a rate of change of curvature as well, so that you can also have very high lateral forces there. So the answer to your question is yes, curves do see a disproportional amount of types of failures because they're L over V, not only over speed. So why, and again, be careful. Positive train control, or ETCS, can stop overspeed
But for example, if the bogie suspension is not working properly and you're getting excessive high lateral forces and low vertical forces due to, say, bogie characteristics, train control systems have no idea what's going on. Train control systems will not find those type of problems. So I always warn people that, don't rely exclusively on train control systems, because train control systems don't always work the best. I mean, they work and they'll prevent this particular accident where they was going 126 kilometers per hour in a curve designed for 15 kilometers per hour. This would have been prevented. The Spanish accident would have been prevented. The Amtrak Philadelphia accident would have been prevented. This is now this particular accident. I think I'm going to come back to it later. This particular accident, a tree fell across the track, and no system would have prevented that one. Okay. All you metro people have been so far been sitting there listening. Well, these are railroad problems, not metro problems. So here is this is a commuter rail operation in Chicago that basically was running on a city track inside Chicago. In this particular case, the train, you can see there was a wheel climb in a switch. Do I have a picture of it? Yes, here. So here, this you can see is a very complex interlocking. Okay, so again, it's very, very easy to lose track of where you are in this particular switch. So in this particular case, there was a wheel climb derailment right over there, right in the curved transition rail, the curved closure rail, sorry. And here again, the train was traveling at 150 kilometers per hour when it entered a crossover designed for 16 kilometers per hour. So this was another messy accident. So in this particular case, the situation was compounded because the train was operated in push mode from a control cab in the rear. So the driver was actually back here. Oh, sorry. The direction of motion here. The driver was back here and he was pushing in that direction. Now, so what happened here? They were actually filming along the right-of-way. Right around over here, there was a crew making a training fill for the railroad. And the engineer was distracted, lost track of his signals. He actually thought that he was being sent on a clear signal straight ahead, in which case his speed would have been appropriate, as 116 kilometers per hour would have been appropriate. He was totally distracted and didn't notice that he was being sent onto the diverging leg, which had a 16 kilometer per hour speed restriction. And he totally missed that. So again, would positive train control have prevented that? Actually, it would have. Basically inattentiveness. Okay. The last human factor accident I want to talk about, and then we'll take a break, is what's called, this is a famous British case. It's an old one, but it raises a whole bunch of interesting issues that I want
at least bring to attention. I just saw the note that somebody just showed up here. Okay. Well, I'm only missing. Is Hadass Benbar on there? Is Hadass, are you here?
Yes, I'm here.
Okay, you came late also. Okay, all right. Okay, so the last case I want to talk about is this is an accident that happened in Paddington Station in the UK. This is the famous Paddington. Let's see if I can mute everybody here. Okay. Okay, everybody should be muted now. So this is by the way, this is the same famous Paddington Station that among other things, Paddington Bear is named after, but it's a major station in the UK. Okay, so this is again a pre-positive train control accident, but it has a couple of interesting lessons, and I want to, and I'm going to go through this because the lessons are interesting, even though this particular accident would probably have been prevented by some sort of positive train control, automatic train control. So this was a really nasty accident as well, about 31 fatalities, and one of the and a nasty one in the British railway system. So this was a situation where this particular train, it was called the Thames train, was crossing over to get into this track. So basically he's doing a double crossover. And it's of course controlled by signals and just everything else. But this particular signal, as we'll come back to later, was known to have problems to it. And this is one of the issues that I want to highlight here as we come to it. So just as we watch this accident, so you can see the Thames train start. It's supposed to be going over 2 tracks. So it starts moving across the 2 tracks. And then all of a sudden, there is another train that's coming along here. So actually, he had a red signal. He should have been going. He came through. He got hit just, or not quite head on, just off the side. That train got thrown up into the air. The other trains were derailed. 30 people were killed from that particular car. Trains were caught on fire, and it was, classical accident. Okay. So in the British system, when you go past a signal improperly, they call it SPAD, or a signal passed at danger, which means there's a danger of signaling. Other railways call it a past red signal. There are other terminology for it, but the British use this particular term, which you'll see elsewhere in the railroad world, or signal past that danger. Okay, so this particular signal which is the signal that controls the operation of this particular train right over there. Has a history of failure. So remember that accident was 1999. So this is the 5 years before that accident. So you can see now, oh, by the way, the driver of the train that passed the signal had just been promoted to operate by himself. So he basically has less than a year's worth of service, actually probably of the order of 1 to 2 months worth of service. So he's an relatively inexperienced driver, even though he passed his qualification exams. So you can see in 1995, there was a problem with that signal. In 1996, there was a problem with that signal. In June 1996, there was a problem with sun shining on the signal. So certain types of signals, you can, if there's really too bright a sun, you can't always clearly tell what the color is. And again, this is one of those signals. 1997, 1998, 1999, 1998, 1998. 3 of them were bright sun. 3 of them were just physically a problem. And by the way, notice in these particular cases, we're talking about very, very experienced drivers. You know, this driver has 34 years of service. This driver has 37 years experience. This driver has 39 years experience. So there was a big history of this particular signal. So in this particular case, the driver was not experienced. Sorry, he was qualified as a driver 2 weeks before the accident. He passed this particular signal, which has a history of problem. So again, the sun was shining towards the signal, and bright sunlight changes this brightness of the signal and the ability to detect the color. There's a term called swamping the signal that occurs here. So in this particular accident, because of its history, there's a real question as to whether or not that signal should not have been corrected previously, should not have been repositioned, moved elsewhere. The driver died, so they never really got the exact details of what happened there. He's one of the 30 fatalities. But the British, so if you recall, they have a very, very strong penchant for dealing with rail management or human factors. They really felt that this was a management or an oversight problem. So when you get to a root cause, so clearly the problem that the accident caused was he passed the signal. So was the root cause signal placement, poor training, poor management, all of the above? Okay. Before we take a break, I want to show you 2 videos, and we're going to come back and talk about these videos in the next one, but I want to give you something to think about. So let me share my screen again. Okay, move this down. Okay, so we're going to talk about this after the break, but what happened here? Anybody want to tell me what happened here? It's look.
Mistake of dispatcher?
Mistake of the
Dispatcher.
Mistake of the dispatcher, if it was the dispatcher, or if this may have been a manual switch. So in smaller sidings, the dispatcher does not always control the switch, but the train crew can actually control the position of the switch. So in this, but you're right. The problem here is the switch is in the wrong position. The switch should have been for going straight, but as you can see, the switch is thrown to get into this particular siding, and so we'll talk about that one in a moment. And let me give you one more, which is similar but a little different.
So let's look at this one. Let's just go. Okay. Which way is the switch set?
Right side.
Right. And there's a train straight ahead, right? So the switch is set properly here.
But there's a red signal.
Yes, there's a red signal. What happened?
The opposite train didn't get that signal.
No, that train is stopped. As a matter of fact, not only is the train stopped, let's go ahead here for a second. Let me just see. I want to show you something. Watch the left side of the locomotive. Watch the left side of this opposite train here. Did anybody see anything happen just then?
Somebody jumped out.
Two people jumped out. The crew. One. What happened here? So what happened here? Let me see if I can show this a little bit.
Terroristic act.
This train was too far forward. Look at the clearance. There's not enough clearance between the track. This train should have been further back. So yes. So this was not this wasn't quite a head-on, but this was a pretty close side swipe. So in this particular case, the signal was proper, but this train crew had moved the train up too far. Okay, let's take a break. Let's take a 15-minute break. Come back about 25-2, and we'll continue and we'll talk a little bit more about operations related type of accidents.
Alan, but you didn't say how to prevent the human factor.
Okay, so you're right. The way you prevent most of the human factors right now is through the introduction of a positive train control or a ETCS type of technology. That's designed to prevent the overspeed, and that's designed to prevent the red signal once. Now, where you run into a problem, for example, there was a very famous accident that happened in Germany a number of years ago with ETCS in place, where they were literally switching the software from one version to another. And there was a short period of a couple of hours when they did not have ETCS working, yet they were operating trains because they were trying to maintain the schedule. So they had switched to basically manual operations, and there was a major accident that happened that way. So the way most human factors accidents are prevented by the new technology of train control. But otherwise, how do you prevent it? By basically rules and training. Because if you notice, all of the accidents I showed you,
the driver did something wrong or the dispatcher did something wrong. They didn't properly use. So that's why that's why positive train control and ETCS technologies have been introduced. But as you can see there, they're not 100%. They're not. They should never be a substitute for replacement. They should be only a supplement to this replacement. In fact, in many parts of the world, train control software is basically considered to be a safety backup. And the primary safety responsibility is not taken away from the driver and the dispatcher. They still maintain the proper safety dispatcher. In other words, the idea is you don't say, oh, we have train control software, so therefore we don't have to worry about that. We have seen time and again, I showed you several accidents today where the presence, even they have the technology in there, something goes wrong. You know, there's an override switch. How many overrides did you see? At least I showed you at least 3 European override accidents, right? Where there was and there has to be an override. And again, my classic example, what happened if the red signal goes bad? What happened if there's a track circuit that goes bad? If the signal's red, you're telling me you can never pass that because it'll only stop the train? You have to have an ability to override it. And so the ability to override is absolutely necessary from an operational point of view. So in a lot of the railroads of the world, train control, positive train control, ETCS, is a safety backup, but it's not the primary. The primary remains rules, training, driver, dispatcher. Okay.
Thank you. Clear.
Okay. Very good. So let's resume now. 22. Many of you may have heard the answer, but not all of you, because I think already it started to break. So I want to make a point that I raised before and introduce it. So the question that Rima asked me was, well, how do you prevent human factor accidents? And the simplistic answer is you introduce positive train control or European train control systems or advanced train control systems, and you let those handle the potential accidents with overspeed and passing a red signal and etc. And the reason that's a simplistic answer is that in reality, you don't really want to shift the responsibility for safety away from the key operators, from the drivers and the dispatchers, and move it to the tech and put the primary responsibility for safety on the technology. So if you actually look at how these systems are designed and you see how they're implemented in many, many, many parts of the world, they're designed as safety backup systems. And in fact, that's the key issue here. The design, they're really backup issues. The primary safety mechanism remains the driver, remains a dispatcher, and remains the basic signaling system. The train control systems are designed to first alert the driver that something's wrong. So all of the systems, be it the German train control system, the European train control system, the positive train control system, the advanced train control system, they all will first give a signal to the driver that says, you're going too fast, or you're approaching a red signal. You're about to go past the red signal. You're going too fast going into a curve. You're going too fast going into a piece of that section of track. Slow down or stop. And only when it does not, when the driver does not execute, when he does not slow down, when he does not stop, either he's distracted or, back to the dead man switch type of scenario where he's incapacitated, he's physically unable to operate the train, then the safety backup system kicks in. And then the system will stop the train or slow down the train, depending on the scenario that you're dealing with. So that does not really detract from the whole issue of proper training and proper rules and proper enforcement of the rules. All are key for the operations.
Question?
Yeah.
What is the difference between automatic train protection and positive train control? What is positive train control?
Okay. In some cases, it's a question of terminology. So if you remember, I mentioned there was sort of there was an evolution of train control systems. So the earlier generations are basically what we call the automatic train stop type of systems. You see them a lot in metros, but you also see the German system that we talked about on a number of the accidents. They were train stop systems. So they're triggered, a lot of those are triggered by passing a red signal. And when you pass the red signal, then automatically something kicks in. Okay, the next generation are what we call the train control systems. And so that's where you have positive train control, advanced train control, European train control systems. They're actually all cousins of each other, but in the United States, nobody's going to adopt the European train control system. So in the United States, it's called positive train control system. Or in North America, it's called positive train control system. In Europe, it's called the ETCS, the European Train Control System. All of those systems are a little bit more sophisticated. They monitor speed, they monitor location. They can tell when you're approaching a red signal too quickly and you're not getting ready to stop. So they can tell the driver, slow down or stop before you get to the red signal. Or you're approaching a curve and you're telling you, and you have to slow down your speed before you get to the curve. Again, I showed you several accidents where the speed going into the curve were 2 to 3 times, 2 to 2.5 times the allowable speed on the curve, and that's that generates the high lateral forces and the high LOV ratios, etc. So positive train control is a terminology we use a lot in North America. And you'll see that same terminology, for example, in Australia, uses the same terminology. A lot of the UIC railroads have adopted the ETCS, the European Train Control System terminology. Now, there is another layer. Now let's get a little bit into the technical differences. There is another layer of differences that we run into where it determines how do you determine the position of the train? How do you determine the position of the speed of the train? And they're divided into sort of 3 parts. Do I use the existing signaling system to tell me how to use it? Do I use information on the track that tells me that? Or do I use GPS to tell me that? Okay, so for example, some of the newer generation positive train control systems use GPS to tell you the position of the train and the speed, and of course you can calculate the speed of the train, but that's not enough. So now what you need is something on the track, some call it a ballista, some call it, there are other names for it, but it tells you what the position of a switch, for example, is. So if you remember the first video that I showed you right before the break, where somebody, I think it was Rima, actually, I think it was you, said that it was the dispatcher who had moved the
the switch to the wrong position. Well, how does the positive train control system or the European train control system know what the position of the switch is? Know it's wrong. So there is a device that's located near the switch that monitors the position of the switch and actually uses radio transmission to transmit the information about the position of the switch to the locomotive, to the receiver and the locomotive, as well as to the dispatching center. So they know the position of the switch. So if that train that we showed you going into the switch where there was a parked train already in the siding, and the switch was thrown to the siding, there's a device that's on the track that provides that information back to the locomotive. The locomotive driver says, I'm approaching that switch, it's in the wrong position, I have to stop the train. Otherwise, I'm gonna hit a train that stopped. So that's a feature we see in ETCS level 4. For example, ETC level 4 really does not want to rely on track circuits anymore. They want to rely on non-track circuit based systems. Some of the positive train control systems work the same way. Other systems like Amtrak, for example, has that has an advanced train control system, ATCS, that makes use of existing track circuits. It's superimposed on top of track circuits. So it gives you more information. Traditional track circuits only tell you there's a train in this block and it turns a signal red. Well, the advanced train control systems not only tell you there's a train, looks at the block signals, they look at the speed of the train, they look at, they can calculate the speed of the train using weight track system based information. They can look at the position of the switches, again, using ballistas or other types of technology that they're mounted wayside, and they enter into that whole logic making process. So I know there's some confusion in terminology. Part of it is political. As I said, the Americans and the Australians do not use European train control systems. They use positive train control systems. Okay. But they're basically doing very similar technology. Most American PTC, positive train control, and most European train control system level 3, for example, are very similar to each other. They use a lot of the same technology. In fact, it's interesting, some of the major manufacturers in the world, like Siemens, for example, manufacture systems for both Europe and for the US, and they use the same technology. It was sort of a long-winded answer, but did I at least try to answer did I give you the answer to your question you were looking for, Rima?
Yeah, clear. Thank you very much.
Okay. Any other questions before I go on? I think it's really important, even though you guys are track people, and we spent a lot of time talking about track. I'm going to go back to track next week. I'm going to talk a little bit about switches and level crossings. But I think it's really important that you understand the broader extent of railway operations, so you know what's the technology, where's the industry going, where are the problems, where are the accidents. No other questions? Okay, I'm putting everybody to sleep, right? Okay.